Good morning, everyone. My name is Mark Abraham. I'm with A&M Industrial. Thank you for joining us this morning. And I hope you joined us today to learn more about steam traps. That's why I joined. Last year, A&M introduced A&M University, where we hosted 25 technical presentations and provided access to more vendors and their products over the course of the day. This year, we have reintroduced it as Virtual A&M University, and this session is part of that Virtual A&M University. For those of you who aren't as familiar with A&M, I wanted to share some basic information. This year, we completed work on our new buyer's guide. The 16-page document presents the products and brands that A&M focuses on for our customers. On the left, you can see the cover. Today, we're going to talk about steam traps, but we also have experts in cutting tools and abrasives, mill supplies, tape and packaging, tools, fluid handling and hose assemblies, pipe valves and fittings, safety products and services, janitorial and cleaning supplies, including sanitizers and disinfectant, material handling and storage, and we also manage customer inventories with our AIM Vendor Managed Inventory Program. On the right is a page from the buyer's guide where it highlights some of the vendors that we are partnering with on the steam side. Over the last few months, we've been focusing with our customers on the products and processes that make our employees safe and keep our facilities operating. We added a page to our website which highlights items that you may need to deal with the crisis, and we have published a catalog there of all the items that people need for cleaning and safety related to the virus. Feel free to visit there when the session is over. We also maintain a video library on our website. Today's session will be recorded. Later this week, we will be posting that recording online with the other webinars that we have already recently presented. For all those who have attended, I will be sending out an email later this week also with a copy of the presentation and also a link to the recording if you want to share it with somebody or listen again to anything that was covered during the presentation. So, today we want to talk about understanding steam traps. We're fortunate to have Tom Lally, who's a technical specialist with A&M, go through his presentation. He'll be covering different types of steam traps, including thermostatic, mechanical, and thermodynamic, and we'll cover some basic sizing of steam traps. Tom Lally is a technical sales specialist for A&M Industrial in the Process Systems and Equipment Division. Tom is a former employee of a manufacturer of steam traps, temperature and pressure controls, metering devices, level controls, and other steam-related heat transfer products. He has assisted many customers in a wide array of industries in the design and engineering of steam systems solutions to improve plant efficiencies and steam energy usage. Tom received a bachelor's degree in chemical engineering from Lehigh University. Again, so during the presentation, I will be watching for any questions, and I will interrupt Tom during the way if there are some questions that occur. And there will also be time at the end for anyone who has questions. We'll have time at the end as well. So now, just give us a minute as I hand over to Tom, and he begins with his presentation.
Good morning, everyone, and thank you for joining us. I am Tom Lally, Technical Sales Specialist with A&M Industrial, and I'm happy to be here to give you a little bit of a background on steam trapping this morning. So I'm going to quickly go through the agenda here. We're going to really start off very basic. What is a steam trap and why is it used? Then we're going to take some time to go through the three basic types of traps by how they operate, which would be temperature driven traps, density driven, and velocity driven traps. After we go through the pros and cons and the features and benefits of the different types of traps, then we're going to talk a little bit about applications. And the three common applications that you'll find in industrial facilities are what we call drip, tracer, and process applications. And then within each area of that steam system, the drip, the tracer, and the process, we'll look a little bit about sizing. And then we're going to save some time. I'll try to save some time for question and answers at the end. Okay, so in a steam system, you might expect there to be just steam in the pipe, but actually there's several fluids in there and medias and other byproducts that have to be addressed in a steam system. Obviously, steam is the main fluid that you want to have in your piping network and in your process. It is the heating medium that has the largest amount of heat per pound mass for various types of utility fluids. So it is desirable to have that steam space occupied only by steam to be the most efficient. But as a byproduct of a steam system, you're also going to have condensate, which is just the steam that has given up its latent heat and condensed back down into a liquid phase. So that condensate is a valuable byproduct, though. It still retains some energy in terms of sensible heat, and it is basically chemically treated and slightly purified water. So as a utility, as a byproduct, you want to recycle that back to the boiler as best you can. So the most efficient steam systems will have as close to or near to 100% condensate return as they possibly can. That's never a perfect scenario, but it's something to strive for. Also in the steam system, you'll have air and non-condensable gases. Now, these are fluids that you want to take out of the steam system as best you can, and it's the function of the steam trap to help you do that. Both air and non-condensable gases, just as the wording says, do not condense. So even if they give up heat or cool down, they do not change phase from gas to liquid in the operating conditions of a steam system. So what they end up doing is just blocking space, and as a major component of the steam system, it could retard the flow of steam going into remote areas of a piping network, for example. They also combine to provide corrosive condensate. Those gases dissolved into the liquid phase condensate will help to form carbonic acid, which will eventually start to attack the metalwork in your steam systems. So those gases definitely need to be removed. Dirt is the byproduct of that corrosion I spoke of. So the better that you can relieve the steam system of the air and non-condensable gases, the better you can treat your steam at the boiler and even in the distribution system. You can help yourselves by reducing the amount of corrosion and therefore the amount of dirt that gets produced in the system. Now, some steam traps will pass dirt, some will not, and we'll look at that a little bit. But as far as the steam trap goes, you really have to think of a steam trap as nothing more than a automatic valve. And the automatic valve has to work based on positive pressure drop. There's some misconceptions in the marketplace that one particular type of trap by its operation will push condensate better than another trap. And really, all traps will push condensate. It's just dependent on the inlet pressure to the steam trap being higher than the outlet pressure to the outside of the steam trap. As long as that positive pressure differential exists, condensate will flow. In a steam system, compared to, let's say, a hydronic system, you don't always have that positive differential, as we'll see. So that automatic valve that's in the steam trap differentiates between steam and condensate and steam and non-condensable gases. And it'll do that based on temperature differences. It'll do that based on density differences between obviously a gas and a liquid, or velocity. The speed with which a fluid will flow through a pipe will vary, or through an orifice will vary, depending on whether it's a gas, which would be a higher velocity, or a liquid, which would tend to be a slower velocity. So the automatic steam trap then closes in the presence of steam, so it does not pass live steam. And basically, you want to be able to allow the steam to fill the space, especially in a process area where it's designed to give up its latent heat. If you allowed steam to blow through a heat exchanger, for example, unrestricted, there would be no residence time for the steam in that space, and your heat transfer would be inefficient. So the steam has to be held in residence to give up its heat. Then when that steam condenses and condensate is formed, you have to have a means of removing that condensate. The liquid phase will block the space. It'll block heat transfer, or it'll slow heat transfer. So that condensate needs to be removed efficiently and recycled, as I mentioned earlier. Then also, depending on how your steam system runs, and we'll look at this a little bit in the application end, the presence of air in your system, either a lot of air or a little bit of air, will also determine what type of trap maybe you would lean to by its operation, so that it can effectively vent out whatever air is present in the space. So the broad categories that I mentioned earlier, thermostatic, it's a thermostatic type of steam trap is operating on a temperature difference. Mechanical types of traps are going to be working on a density, level control, typically type of difference between steam and condensate. And thermodynamic is a broad term covering a lot of different types of traps, impulse traps, what have you. But the thermodynamic, they're all basically working on a velocity principle. And we'll look at that in a little further detail. We're going to start off with the thermostatic. It's probably one of the earliest types of traps ever manufactured, back in the late 1800s, early 1900s. And these thermostatic traps, again, work on the temperature difference between steam as a gas and condensate as a liquid. Now, everyone knows that saturated steam curve will give you, for any given steam pressure, there's a corresponding steam temperature. And directly at condensation, the condensate and the live steam occupying the same space will have that same temperature. So these traps have to work with, in order for them to hold back live steam, they have to be able to sense a slightly lower temperature and operate at a slightly lower temperature than the saturation steam curve. And they do that, these mechanisms do that by either a capsule or a bellows fill, or bimetal plates, which is over here on the bimetallic trap. And all those will sense a temperature cooler than live steam and will tend to close the trap off prior to reaching that live steam temperature. Since these are temperature sensitive traps, all of them, as you would expect, would be wide open when they're cold. So from a startup standpoint, air and non-condensable gases being colder than live steam, and cold condensate being colder than live steam, would tend to freely flow through the trap. So startup on these traps is fairly straightforward. Again, based on the principle that there's a positive pressure differential. Once you establish that positive pressure differential, condensate will flow pretty freely through the trap on startup. Once that condensate starts to elevate in temperature and approach live steam temperatures, then that bellows, capsule, or the bimetal plates will respond to the hotter temperature. And in the case of the bellows or the capsule, it'll expand out like an accordion and it'll drive the valve head onto the seat. The bimetal plates will expand at different rates and create kind of a clamshell effect and pull the valve stem and valve head up onto its seat, closing off the trap. And at that point, those traps will stay in that position until heat is lost from the body of the trap, and the condensate surrounding the bellows or the bimetal elements can cool off, and that'll open up the trap again and allow more condensate to pass. But you would expect that while that time delay is happening, while the heat's being lost off the trap body and the condensate's cooling down, that you're backing up some condensate towards the steam system, which can be desirable. It can be detrimental to your system. It's just something that you have to understand with a thermostatic trap, that's the type of operation. They tend to discharge continuously. Sometimes they'll dribble. Sometimes, depending on the load, they'll just pass on a continuous basis. These are typically, they can be used outdoors, especially if you can install them in vertical piping. They tend to be self-draining if allowed to self-drain by gravity in a vertical position. They will open up again when cold and tend to drain condensate from the system. Liquid expansion is just one of the specialty types of traps in the thermostatic family. In this case, there's a liquid-filled bellows, but if you'll notice, that's on the downstream side of the valve head and seat assembly. And that thermostatic bellows is then exposed to atmospheric temperature. So this type of a trap is only going to operate at or below 212 degrees. So you would expect it to back up a fair amount of condensate into the system. But that's okay, especially for, if you're looking for a crude type of temperature control device. So let's say you have an outdoor storage tank filled with water, maybe a fire protection tank, and you just want to have a steam coil in the bottom to keep it from freezing. This type of a trap can be set to discharge condensate, let's say at 150 degrees or 120 degrees, something along those lines, and you can do a crude form of temperature control on the storage tank to keep it from freezing. Once again, it has all the same characteristics as the other thermostatic traps. It'll be wide open on startup, so it'll be venting air, non-condensables, and cold condensate freely. So I talked about the saturated steam curve, and this is the relationship that you need to understand with thermostatic traps, is that they will always operate at some temperature below saturation. So condensate will be discharging somewhere below the saturated steam curve, and therefore backing up some condensate towards the system, back towards the system. The actual delta T is going to vary by trap manufacturer. Some manufacturers will do what they call a near to steam temperature profile, which is, for the most part, primarily distilled water inside of a capsule. So it's going to have a boiling point very close to your live steam temperature, and it'll tend to back up less condensate that way. In other cases, they'll use an alcohol and water blend, which will drop that 212 degree boiling point at atmospheric pressure down to maybe 20 or 30 degrees below any given saturation temperature. So again, that's not necessarily a bad thing as long as you understand that that's the operation of the trap. So we're going to move to the mechanical traps. And in this case, again, these are working on the density principle, density difference principle. Steam as a gas is much lighter than condensate as a liquid, obviously. And so you're going to get inside these products, you're going to get more or less level control. So there's going to be some sort of buoyancy, some sort of component in there that provides buoyancy. That component's attached to a lever arm and a pivot point, and on that lever arm is a valve head, which closes off on a valve seat. And the presence of condensate is then an essential point in getting the trap to open and close. So the first one we'll look at is the inverted bucket steam trap. This is a very basic trap. In this case, it uses an upside down bucket or coffee can or what have you that's attached to a lever arm, again with the valve head on it. And that upside down bucket provides a pocket where a gas can cause the bucket to have buoyancy when it's surrounded by liquid, and allow that bucket to float upwards towards the top of the trap. By having that bucket float upwards towards the top of the trap, the valve head is pushed off against the seat, and that shuts the trap off. So the valve head and seat are up at the top. Flow would come in down through the bottom of the bucket, and then flow out through the top of the trap and out the outlet side. So steam as a gas obviously will float the bucket, since it has a lighter density than condensate. But in the same respect, air and non-condensable gases will float the bucket. The problem with air and non-condensable gases is they're non-condensable. So all things being equal, if the bucket were to float up with air, close the trap off, the trap would then just lock closed and never open again. So all trap manufacturers install and drill a small bleed hole in the top of the bucket, and that there is intended to allow the air and non-condensables to bleed out from the bucket, allow the bucket to drop, to lose its buoyancy and fall, allow the trap to open, and allow the trap to clear the air. You can imagine that that's probably a slow process, and in fact it is. It's not a mechanical failure of the trap. It is just a condition that the trap is going to work under. It's what we call limited air handling capability, but given time and given the opportunity to clear air, it will do so. And will return once the air non-condensables are clear, it will return to normal operation and work as a very effective steam trap. With inverted bucket traps, you do need to have condensate present inside the body to create buoyancy around the bucket. You do need a little bit of system pressure also to help overcome the weight of the parts. So in terms of operation, you want to be careful about oversizing an inverted bucket trap, because if there is a insufficient amount of condensate coming to the trap, it cannot maintain a liquid seal around the bucket, and the trap will do what we call lose its prime, which again is not a mechanical failure. There's nothing wrong with the product itself. It's just an insufficient amount of condensate to maintain a liquid seal around the bucket. Given time again, it will reprime itself if there's sufficient condensate in the system. It will reprime itself and return to perfect operation. Again, it's just something to consider if you have a variable condensate load, that you have to be a little bit careful about sizing. And within respect to a 1-hour presentation, we're going to go into a little bit of sizing, but not all the nuances. So I apologize, but we can certainly address any questions or concerns or applications that you have on a one-by-one basis. The second type of density operated trap is called a float and thermostatic steam trap, or float operated. In this case, there's a sealed stainless steel ball float that's attached to a lever arm, which has the valve head on it and a pivot point. And the buoyancy of that float on the liquid level pulls the valve head off its seat and back onto it. So it opens and closes at the same time. Most trap manufacturers rate the capacity of a float and thermostatic trap strictly on the orifice size of the float mechanism. So the rated capacity in any manufacturer's table will be based on the float mechanism itself. The interesting part of an F&T trap is the fact that there's got a T in the name, and there is a thermostatic, temperature sensitive, secondary orifice built into the trap body. And that there is intended for just an air vent and possibly cold condensate startup. So this trap combines actually two traps in one. The float mechanism is your primary discharge point. Your air vent is for startup conditions. So anytime you would have a startup condition where air and non-condensable gases are present and cold condensate is present from just a warm up of the mass of metal, you have basically two orifices to allow all those fluids to discharge through. Where condensate was necessary to keep the bucket trap primed to allow the bucket to float and shut off the trap, it's converse in a float and thermostatic trap. The main orifice, the float operated orifice, is at the bottom of the trap in this case. And it's, for the most part, liquid sealed under the liquid level of the water. So these traps can work on basically a dry line with very little condensate load. And the weight of the parts in this case will close the trap, where the weight of the parts in an inverted bucket trap opens the trap. So that's the main difference between the two density styles of traps. In both cases, as you can see from the pictures, each trap body retains condensate. So you have to be a little bit careful in applying these products outdoors where you're subject to freezing, for example. So both of these, if given the opportunity with the system shut down by purpose or by accident, if these are retaining condensate, they will be subject to freeze damage, depending on the body materials. If it's cast iron, for example, they will more than likely freeze and crack. In both cases, the mechanical and density types of traps, because they're working on a liquid level, they're going to be sensitive to load changes, and they're going to more or less continuously discharge. The inverted bucket trap can cycle on a lighter load condition, but as soon as you start to get into a heavier process load, both of these traps will more or less be continuously discharging with really no shut-off cycle to them. And looking again at the saturated steam curve, since both of these traps are working on an interface between the steam and the gas and the condensate, they're going to be discharging condensate virtually at steam temperatures. So there should be little to no backup condensate back towards the steam system when using a density style trap. The last trap type we'll look at is the thermodynamic steam trap. These are, depending on the manufacturer, they're made in all different types of orientations and configurations, without strainers, with strainers, what have you. But in general, they're all working with one moving part, which is a flat stainless steel disc that moves up and down off the seats in the body of the trap. So the principle of operation here with a thermodynamic trap, again, is velocity based. So we're going to be sensing, the trap's going to be sensing the difference in the speed of flow of gases over a surface compared to liquid over the same surface. So the principle is actually it's called Bernoulli's theorem, and it's the principle that creates lift in an airplane wing. So the velocity of air passing over the top of the wing is flowing at a speed faster than the bottom of the wing, and the faster velocity on top actually creates a low pressure zone, and the wing is actually lifted in space. So the same principle occurs here with the bottom side of the disk. As condensate flows through the trap, system pressure just lifts the disk up, and condensate flows through freely. As gases start to reach the throat of the trap, they start to flow at a higher velocity underneath the bottom side of the disk, and that creates that Bernoulli's effect, creates the low pressure zone. The disk is actually starting to get sucked down towards the seats, pulled down towards the seats. In the case of steam, when you have flashing occurring inside the throat of the trap, those flash steam bubbles is really what's getting the trap to operate. And as it's pulling the disc down onto the seat, at the same time, some of those bubbles of flash steam jump up to the top side of the disc. You have a difference in surface areas to apply force to, and those bubbles, those partial pressure bubbles of flash steam, exert a downward force onto the top of the disc, and that gets the disc to snap closed. So this type of a steam trap is definitely a cyclical discharge. It's going to blast open for a period of time and then shut itself off. So once the trap is closed and those partial pressure bubbles of flash steam are holding the disc closed, you need a time delay to allow the heat energy to be lost off the top of the cap. Those flash steam bubbles collapse. The force holding the disc down disappears. System pressure once again can overcome the weight of the disc and pops the trap open for the next discharge cycle. So if you think about it, with steam as a gas, flash steam as a gas closing the trap, air and non-condensable gases will have the same effect. And in fact, most thermodynamic traps can be used on compressed air systems as liquid drain traps for that very reason. So in a steam system, you have to be careful. Similar to the inverted bucket trap, it's not a mechanical defect to the trap. It's just a characteristic of its operation. And the trap will clear the air eventually. And there's never a perfect metal-to-metal seat, and the air will dissipate through the trap, and the trap will go back into normal operation. So it's not mechanically failed. It's just what we call airbound. And that's a condition that's kind of typical on startup. But if you know that, and you can plan for it, and you can tolerate a time delay, trap is perfectly acceptable for a lot of applications. And then looking again at the saturated steam curve for a thermodynamic trap, it's going to be discharging pretty much maybe 2 degrees below saturation temperature. There's always going to be a little bit of backup behind a thermodynamic trap. It's as soon as the pressure drop occurs inside the throat, you'll always get flashing. So that hot condensate will flash. That'll tend to close the trap off before live steam reaches it. So there's always going to be a little bit of subcooling, and like I said, about 2 degrees. But it's going to be what we would consider a hot discharge trap. So that kind of slide summarizes the characteristics. So we use two characteristics to kind of describe the trap. The amount it subcools, or the amount of temperature difference it's going to operate below saturation, and its ability to handle air and non-condensable gases. And if you look at the chart here, you've got the basic trap types: thermostatic at the top, balanced pressure and bimetallic and liquid expansion, float thermostatic and inverter bucket at the bottom, obviously. And it gives you the usual discharge patterns. Blast action, so the trap is definitely a thermodynamic trap, for example, is definitely a cyclical open and closed type of operation. You would expect then a small amount of condensate backup. Balanced pressure, thermostatic, very light loads, it will tend to cycle on and off because the time delay that it takes to lose temperature will allow condensate to back up, and it'll blast out and then cycle back off. On heavier loads, it'll be more or less a continuous dribble, as would be the bimetallic and the liquid expansion thermostatic traps. They would be continuous dribble in operation. But as we mentioned, because they're temperature driven, those three traps are temperature driven, they're all wide open on startup, so they're all excellent air vents. And then lastly, the two density traps, the float and thermostatic and the inverted bucket. Float and thermostatic is more or less going to be continuous discharge. It's going to be very difficult to find that trap fully closed off under most conditions. It's always going to be discharging. By virtue of the thermostatic air vent in there, it also happens to be an excellent air vent and non-condensable gas vent trap for startup purposes. Inverted bucket is going to be on light loads. It's going to tend to cycle similar to the thermodynamic trap. It'll cycle, never fully closed necessarily, but it'll tend to cycle flow on and off. Under heavier loads, it'll act more like the float and thermostatic, and it'll just be a continuous discharge. Because there's no real air vent in an inverted bucket trap, nothing practical anyway, it is going to have a limited air handling capability.
Tom, I have a question.
Yes.
That was presented. You mentioned all these different style traps, but you didn't mention universal style trap. Can you explain the differences between universal trap and what you've been talking about so far?
Sure. Universal series of traps, most manufacturers now provide a technology that allows you to put in a two component steam trap. One being some sort of a connector piece, a pipeline connector piece, which has a flange and a 2-bolt connection on it, and then a trap module. Any of the trap modules that we've talked about here, except for the liquid expansion, would be available as a bolt-on piece to that pipeline connector. So we'll see that in a couple more slides, but what it does is gives you the advantage of being able to remove a trap quickly from a steam system without necessarily breaking pipe. So you can apply any of the technologies, like I mentioned, except for liquid expansion, to that connector series, and we'll look at that in a minute here.
Okay.
But thank you for the question. Okay, so now we're going to look at applications real quick. Unfortunately, it would be great if there was one universal type of steam trap that could work in every application. Sadly, that's not really possible. Different operating conditions, different load conditions, different piping arrangements dictate that there's no one solution to every application. So what we're going to look at here is what the application is going to require the steam trap to do. And then at the end, we're going to kind of I'm going to bring together what the trap's characteristics are what the application characteristics are and marry the two together so that, gives you some sort of a guidance as to what type of trap might work best in what application. So from steam main drips, these are the common applications in every steam distribution system. You have to be able to drain the condensate out of a steam main for energy efficiency reasons, for safety reasons. I don't know if any of you have been around a steam main when it has been experiencing water hammer. It's not a very comfortable situation to be in when the pipe's jumping off its supports. It can be very dangerous. So you need to be able to maintain as dry a line as practical in a steam distribution system. So these drip pockets and drip traps are placed strategically throughout a distribution system in a horizontal run of pipe, maybe every 200 to 300 feet, at changes of direction, especially vertical changes, risers, the entrance to an expansion loop, which could be vertical or horizontal. Certainly at takeoffs, as it's shown on the right side of the slide, where you're feeding a steam control valve or a piece of process equipment. The last thing you want to do is take off from a steam main and go and elbow directly into a control valve. That control valve is not going to last too long in service without clean, dry steam flowing through it. So the main thing with drip legs, number one, in terms of piping layout, is just to make sure the pocket's sufficient to allow condensate to drop in by gravity. So for a pipe, let's say up to 6-inch diameter, you want that drip pocket below it to be 4 inches, nothing less than 4 inches. So if you have a 2-inch pipe, you have an equal size T in a 2-inch pocket. 6-inch pipe, you can use a reducing T in a 4-inch pocket. Above 6-inch, then you want to go maybe a pipe size or two smaller, nothing ever less than 4-inch, but kind of nominally 2 to 3 pipe sizes below. So if you have a 10-inch diameter steam main, you probably want to have a 6-inch diameter drip pocket. So the other thing with the drip pocket is you want to have sufficient length coming down from the steam main to create what's called a hydrostatic head on the trap inlet. So on startup, if you're starting that steam main up the first time, you have to bring the mass of metal up to the operating pressure and temperature of the steam, the desired conditions of the steam. That's the worst case for condensate creation, and it occurs at the least amount of pressure. So once again, steam traps are nothing different than any other automatic valve. They need a positive pressure drop to create flow. So that vertical drop, that L dimension, starts to give you hydrostatic head pressure on the trap inlet under those startup conditions. The other thing that's shown in here at the bottom, drain valves. You have a mud leg where the trap comes off. That mud leg, obviously, by its name, will collect dirt over time. So those drain valves should be exercised probably annually, so to keep that drip pocket clear of dirt and debris. The other reason for that drain valve is for a startup. If you pipe everything correctly, and we don't have time to go into the details of that scenario, but you can literally go into the boiler room, flip a switch, and at 3 in the morning, 4 in the morning, and have your steam system come up to pressure and temperature naturally, and have all the condensate drain out, and do what's called an automatic startup. Very, very few steam systems are piped that way, unfortunately. So most of the time you have to do what's called a supervised startup. For safety purposes more than anything else, you need to go around and open up those drain valves and allow that cold startup condensate and air and non-condensables to pass to waste through those drain valves to allow some pressure to build up in the steam main, and then go back and close those drain valves and allow the trap to take over the job of clearing the condensate. That's what's called the supervised startup. And by far, the more safer way to start up a steam distribution system. And again, the way most are piped, the more practical way to avoid water hammer. These two charts here are basically just give you a comparison for a startup condition and a running load condition for a given steam main. So if you look at it, we're looking at an 8-inch diameter pipe at 100 psi. To start that 8-inch pipe up, you have to bring again the mass of metal up to 338 degrees. That's the temperature of 100-pound steam. You have to raise the temperature of that entire piping network to that point. We're predicting about 100 pounds of condensate per hour per 100-foot of linear run of pipe. So if you're doing an automatic startup, you need to size the trap for that kind of a condensate load, 100 pounds an hour per 100 feet. So if your drip pockets are every 200 feet, you would double that. Steam trap would have to handle 200 pounds an hour. At the bottom chart is the same 8-inch pipe at 100 psi, but now everything's up to temperature. Everything's warmed up, and now it's what we call a running load condition. And you can see that load has dropped off more than half. So if you're doing a supervised startup where you're blowing off all that startup condensate, then the steam trap only has to really handle 41 pounds an hour per 100 linear feet. In any case, what a rule of thumb that I can tell you about drip traps is that by and large, if you canvass all the manufacturers that are out there and you look at an inverted bucket trap, or you look at a thermodynamic trap at 100 psi, and you look at these kind of load figures that are in these charts, you're going to find that virtually 99% of your applications, a 1/2 inch or a 3/4 inch size steam trap is all you're going to really need. They're going to do on average 400 to 600 pounds an hour, let's say, depending on the manufacturer and how they design it. But there's going to be a pretty good safety factor on the trap capacity versus these loads. There are always going to be exceptions, and we can talk about those individually, but by and large, 1/2 and 3/4 inch is all you really need for a steam trap size. The one thing you don't want to do is if you have a 2-inch main and you make a 2-inch pocket, you don't want to elbow into a 2-inch steam trap. I can guarantee you that the trap's not going to last you very long in service. You do not line size steam specialty products, generally speaking. So you wouldn't do that with a pressure reducing valve or a control valve. You don't do it with a trap, which is an automatic valve in itself. So same rules would apply. Second one is what we consider steam tracing. That's an industrial practice, for freeze protection or for product protection to keep products in outdoor piping from solidifying. The best analogy in let's say food or pharmaceutical applications would be steam in place requirements, where you're sterilizing product transfer lines, or you're sterilizing in place reactor vessels, things of that nature. So in these cases, what you're looking to do is to achieve certain temperature on the product side, or again in the sterilization, you're looking to say, for example, 121 degrees Celsius, so you can sterilize in place piping networks. These kind of conditions, you're looking at primarily, thermostatic traps or thermodynamic traps. If you were working in an asphalt plant or a sulfur plant in a heavy industrial complex, those products will set up well above 250, 300 degrees you want to have a steam tracer or a steam jacket that's completely full of steam. You don't want any potential for condensate to back up. You might want to consider, in a critical application like that, you might want to consider a thermodynamic trap. If you're in a food and pharmaceutical plant and you're steaming in place process piping and process vessels after every batch where there's a lot of air and non-condensables to consider, well, the thermodynamic trap would work, but it may not give you the best startup time, or it might delay the process. In that case, a thermostatic trap might be better suited, as long as you understand, again, that a thermostatic trap will back up condensate towards your process piping. So if you maintain a good distance, if there's a good distance between, let's say, a thermocouple that you're using to prove out sterilization temperatures, you put a little bit of distance between that thermocouple and the trap inlet so that you can accommodate backup without flooding the thermocouple. So everything can be handled, and 9 times out of 10 in the food and pharma industries, we see thermostatic, balanced pressure thermostatic traps by and large used. Another advantage of that type of trap is that it can be manufactured in a sense with more of a sanitary design. Nothing is ever crevice free with a steam trap, but you can manufacturers make the balanced pressure thermostatic trap specifically in sanitary body conditions, tri-clamp end connections, a tri-clamp body connection where the two pieces fit together, and it can be easily cleaned and readied for the next batch operation. So for tracers, the main thing is you want to just keep them individually trapped. The top picture here, figure 26, shows 2 individual tracers trapped by one trap. Process we call gang trapping. It's not recommended. There's always a pressure difference between the two circuits. Tracing applications, if you are doing industrial work, you can start to look at manifolds for the supply and the collection of condensate. And in these cases, you are getting an opportunity to clean up your piping network. It won't be so much of a spaghetti look, with traps just hanging in air. It cleans up the installation and makes it a little bit safer for you. This is what we were talking about earlier with the question about the universal traps. These are typical trap stations that are available by, most of the manufacturers are offering these types of technologies. And they can be flanged, they can be threaded, but in most cases you have inlet and outlet isolation, you have inlet bypass, so you can drain upstream but still isolate the trap. You can blow down for testing, you can blow down strainers if they're built in, and as the picture on the right, on the left shows, the trap module would have a 2-bolt connection to the trap station. So you can put thermodynamic, thermostatic, float thermostatic, any of the different types of traps would universally bolt to the connector. So the advantage here is it gives you a nice compact installation, and it eliminates a lot of the leakage points. A conventional trap set, especially in threaded joints, all these connections up at the top are potential leak points, which you don't have at the manufactured trap station. Finally, with applications for process equipment, this is where you want the steam to condense to give up its latent heat to the process. So you're cooking something, you're heating air, you're heating water, whatever you're doing, this is where you want the steam purposely to give up its latent heat. By and large, these are all either temperature or some other secondary process condition. They're all controlled by temperature, pressure, or maybe flow on the secondary side. So there's always a steam control valve on the inlet going into the space and then a barrier for heat transfer from the hot side to the cold side. These applications, it's most important to have condensate drain out of the steam trap by gravity. These tend to be either batch operations. They could be continuous, but they're going to have different load changes. They're going to have different load demands on the process side. So the steam condensate loads are going to vary all over the place. But with the surface area of the heat exchangers generally being constant in most applications, the only thing that can vary to give you heat transfer is the temperature of the steam. And when you vary the steam temperature, you vary the steam pressure. So whereas a drip application, you have constant pressure, a 100-pound steam main, you always have 100 psi on the inlet of the trap. With process applications, because of that modulating control valve, you don't have a constant steam pressure at the inlet of the trap. That's why it's important to have the traps drained by gravity to a vented condensate system. And you also have to have a drop in elevation from the equipment outlet to the steam trap inlet. And there again, you're creating a condition where you allow condensate to collect in that leg, vertical leg, and create hydrostatic head pressure on the trap. That hydrostatic head pressure will allow the condensate to flow. But you'll also notice at the top of the exchanger, you have a vacuum breaker and basically an air vent. And because steam collapses in its space, it will draw a vacuum once it condenses. So as long as you have vacuum at the inlet and atmospheric pressure at the outlet of the steam trap, you no longer have a positive pressure differential across the trap. So the vacuum breaker is placed there to allow atmosphere to be on both sides of the trap, and then you work on the hydrostatic head pressure of the steam trap. So in this example, we're just heating steam with water. There's a rule of thumb equation that most manufacturers use. If you have a flow of water going through an exchanger, it's the gallons per minute divided by 2 times the temperature rise on the water side. And that gets you into a rough neighborhood of what the condensate load is on the system. You can use that for sizing the steam piping, the condensate piping, the control valve, the steam trap as a rule of thumb. So most manufacturers publish also additional rule of thumb formulas, and then also some specific formulas. If you want to get into the engineering units and want to do an exact calculation, the exact formulas can be used. What you'll notice in most cases is you have a true latent heat value underneath the equations, so you can take the actual steam pressure and its corresponding latent heat and use that effectively in the equation, and it'll give you a more precise steam flow calculation, and whatever goes in with steam comes out as condensate, so it's the same. Steam in, condensate out would give you the same flow rate. Safety factors, are going to vary by manufacturers, but most of the time you're looking at anywhere from most recommendations are a 2 to 3 times safety factor. So if you have an exchanger, in the example before us, we had an exchanger that was rated for 855 pounds an hour. If we look at the safety factor loads, we're looking at, let's see, let's take it as a storage heater. 2 times safety factor. So you would multiply the 855 by 2 and then look for a steam trap in a catalog that has that capacity. there again, with that modulating control, you have to be careful about what pressure differential you use. And in most cases, for process applications, you do use a half a PSI. So lastly, to kind of go through the applications and then the trap requirements. So the applications are at the bottom: drip traps, drip applications. The discharge, you don't want to back up condensate deliberately into the steam main, but you can afford a little bit of backup. Continuous or intermittent discharge is okay. You want as little subcooling as you can, but in terms of air handling, unless you're starting that steam main up 3 o'clock in the morning every single day, you once you start it up, there's very little air, non-condensables to be concerned with. So we wouldn't be too concerned about a trap that had limited air handling capability. Critical tracers and tracing and steam in place applications. Tracing, in an industrial, that's usually on in the fall and off in the spring. Once again, you don't have a lot of air to handle. If you're doing sterilization in a food and pharmaceutical, that's more batch operation there. You'd have more air to be handled. So you'd have a steam trap that would be able to handle air better. In most cases, you want a little bit of backup is not too critical in those applications. Process, you want to have continuous discharge. As fast as that steam condenses, you want to have it drain out. Very little subcooling, and those types of things, again, are either going to be batch or going to have air vacuum breakers attached. So you're going to have a lot of air to deal with in process. So you want to have a steam trap that has excellent air handling capability. And then you look at the top side of that chart at the balance pressure bimetallic, the thermostatic traps. They do back up, so you have to be careful, but they're all excellent air vents. Inverted bucket doesn't back up condensate, would be good for process or drips, but it has limited air handling, so you want to be careful applying it to a process. Float thermostatic, virtually no backup and an excellent air vent. And 9 times out of 10, a manufacturer will recommend F&T for a process application. And then the disc traps, thermodynamic traps, they're intermittent. They will back up a little bit, but in a properly sized steam main, they're not going to be a problem. But they are limited air vents, so you have to be careful on startup. And that's pretty much the presentation.
Okay. Well, thank you very much, Tom. Are there any other questions? I don't see any other questions at this time. If anybody has any questions, if not, then thank you very much, Tom, for the presentation.
Thanks,
I
Mark.
appreciate you taking the time. It was very informative. And again, everyone will get an email from me. If you have any questions, you can email me when you get the email from me with all the information from the presentation, as well as the link to the recording. Thank you very much for joining us this morning. Have a good day.